Can you believe this much has happened and it is still only day one? So I get asked a lot in the hallways when I talk to people about the whole idea of engaging more, of networking more when they're at a conference. People say, Tom, you know, I have so much to learn, I have so much responsibility, I already have enough friends. Why? Why is this so important? Well, it's because you've made the investment to be here, and this is PLM world. This is not a junior high dance. Now, some of you chuckle when I say that, and the reason for that is most of us remember the junior high dance. Remember, the girls were on one side, the boys were on the other, everybody was in their cliques, and the trains never met. But while we're here at this group, we should be talking to each other because, as I said, this is not a junior high dance. This is PLM World 2015. That is a junior high dance. Now, this little boy messed up because he didn't ask the pretty girl next to him any questions. Who knows what he could have learned if he just started with hello and built a conversation? Maybe he could have learned, I don't know, maybe that girl's a black belt in karate. Or maybe she's been to 15 countries, including setting foot on the African continent. Or maybe the day before that picture was taken, maybe she was accepted into a magnet high school that is the seventh top math and science high school in all of America. But that kid doesn't know any of that because he never asked my daughter a question. Now, shame on her, because she's my daughter. You would have thought she would have read my books or something. She could have talked to him. But I want to challenge you tonight at Gillies and tomorrow morning and everywhere you go, turn to the person next to you and introduce yourself and have that conversation. Because if they had chatted, maybe they would have become great friends. Maybe now he would know 4 years later that she's been accepted and is off to college at Carnegie Mellon next year. But he doesn't know any of that because he never had that conversation. Now, a little side note, I speak to over about 20,000 people a year, and my daughter has absolutely no idea I use this photograph. Because think about it, if you were an 18-year-old about to leave for college, would you want 20,000 people a year knowing about this photo? And by the way, don't take a picture and tweet it. No, don't do that. Because all it's going to do is make her mad. And she would be like, Dad, really? And I'd say, look, it gets a really big laugh. And then you know what she would do? She'd demand a commission. So, we are going to have another great session right now. But a couple of reminders for the afternoon. Do not forget about Gillies tonight. This is going to be a great opportunity to have some fun, let loose, and network and make connections. The buses will be leaving from the lobby level starting at 6:30, just past the draft bar. And the PLM board members, they are very eager to talk to all of you, and they're wearing those blue shirts that we talked about. So make sure that you're getting the chance to go and chat with them because they want to talk to you. And stick around till the end of this session. After our speaker, there are prizes. Oh yeah, and I'm talking like an iPad Air 2 and an Xbox One, not just crummy prizes, really good prizes. We're gonna have a drawing, but you have to be present. You have to be present to win. So now I'd like to invite a special guest up here to introduce our speaker because they have been friends for over 10 years and they actually went to University of Cincinnati together, and keeping with our space theme, they were there at the same time that Neil Armstrong was there as a professor. So they've known each other for a long time, and Dr. Jan Loredan is the Senior Vice President in charge of simulation and test solutions for Siemens PLM software. Dr. Loredan joined Siemens following the acquisition of LMS by Siemens in 2013, where he served as Chief Technology Officer since 1984. And he's going to introduce our speaker today. Jan?
Thank you, Tom. So thank you, Tom, for letting me be Tom for just two minutes. And good afternoon, ladies and gentlemen. It's really an honor and a pleasure for me to introduce the keynote speaker for this afternoon, to introduce to you Craig Brown, who is General Motors PLM leader. And you should know indeed that Craig is one of my most favorite aerospace engineers. You know, like Tom already mentioned, we went to school together. But what really makes him special is that he is an aerospace engineer working at a car company. And it's not that he is trying to make cars fly, although I can tell you I have had the opportunity to be on the proving grounds at GM in some of the performance vehicles of GM, and I can tell you that some of these vehicles get pretty close to exactly doing that. But what Craig is all about is actually to drive development processes within General Motors to make sure that those development processes, quote unquote, fly, and that they support the innovation that has to go into vehicles these days. And you know that a lot of that innovation has to do with, you know, more controllers being integrated, more software. And as a result of that, the subjects of systems engineering and model-based systems development, model-based development, are moving more and more in the forefront of those development processes. And actually, I've had the opportunity to work with Craig for almost 10 years on the subjects of systems engineering, model-based development. And I can tell you that he being an aerospace engineer, he knew a lot more about that than I did 10 years ago. So Craig, I did learn a lot from you over that period. So let me welcome Craig on stage, and I'm sure we're all ready to listen to his presentation on model-based systems engineering and PLM. Craig?
Thank you. Now, stay here.
I'll stay here.
Oh, good. That's that. Everybody know what that is? Does anybody not know what that is? Okay, I can barely see hands. Okay, close your eyes.
They are closed.
Introduced this weekend, the Camaro 6, not the Corvette. And what you need to know is those things aren't possible. Those kinds of sounds aren't possible without tools from Jan's company. It's really, really, really fun to do this. Everybody that doesn't want to listen to me, start Googling Camaro 6, because that should keep your attention. And figure out how many aluminum parts it has. Figure out how well it performs. Where did Tom go? Tom, you need to go look at the specs. It's better than your Mustang. Anyways, I'm here to talk about something else, okay? So here we go. You've seen this. Several of you I've talked to in the past, and you should know that everything starts with great products. General Motors has been around a long time, and we've had a storied history. Sometimes the story's not as good as they are right now. And we're quite happy with the progress we're making in terms of products. We're quite thankful to all of you in the United States for helping us through our bankruptcy. And I'm here to talk about what we're going to do next. Model-based systems engineering. Oh, by the way, this is the Camaro 5. Because I was traveling here, I couldn't get a picture of a Camaro 6. Anybody found it yet? All you got to do is Google it. You'll get it on your phone. It's all over the place already. It was introduced Saturday at Belle Isle in Detroit, and we hope you really like it. It was made with model-based systems engineering. And what I want to talk about is how that and PLM need to work together. I'll hit you with a couple topics. I know all of you want to not be here very long as the last topic of the day. So maybe I'll just hit you with a few points that you may not know about in the automobile business. All of you know the models part, but I want to show you something you may not know. Give you some examples of systems engineering as we do it in controls, embedded software. And then I'm always, and those of you that have known me a long time, I always have something to say to the tool suppliers. So I have something to say to the tool suppliers, all of you, not just the folks from Siemens. And then I want to end with a couple proof points on systems engineering and what we're doing at GM. The global fuel economy and greenhouse gas requirements across the globe are intense. Read this chart from whatever country you're from. Take a quick look at either the number of carbon dioxide milligrams, or look at the fuel economy. In this country, we measure fuel economy. In 2025, the average fuel economy of all cars needs to be 54.5 miles per gallon. Have any idea what it is right now? For small cars, it's in the 40s. Gosh forbid if you have some big cars, because they're still in the high 20s, maybe low 30s. In a mere 10 years, which means we've already started the planning, already started some of the engineering development, we need to be at 54.5 in order to sell a product here. The United States isn't particularly bad. Look at across the globe, where there are similar objectives in every country. And in particular, notice China. Do you realize where General Motors sells most of its vehicles? It's not here, it's in China. That happened a few years ago. Okay, and the other thing, how much energy do you think, fuel tank into the engine, how much of the energy do you think gets to the wheels? This might surprise you. The answer is the answer 3 years ago, about 23%. That's an awful lot of inefficiency. Where did this 73% go? Well, it goes to things like friction and then heat loss. The opportunities to keep improving internal combustion engines are quite easy to see. Get rid of those efficiencies, whether it's thermal management or whether it's friction management or so on. Of course, you can regenerate some of the energy, and we do that in the hybrids through regen braking and other things. One of the first places we used the Imagine tools, or what is now part of the LMS suite, were in our transmission and drive lines, and we were taught by other people to do that, but once we realized the benefits, we started getting efficiencies through the control systems for transmissions and drive lines. Optimization in the vehicle has to be at a system level. It has to go across all aspects of the vehicle. If we can lightweight the body a bit, put high-strength steel, maybe other materials soon, where those crash zones are to protect the occupant, the lighter we can make the body, then we can make the structure lighter. If you can make the structure lighter, the whole chassis becomes lighter. Then the brakes become smaller. Then the wheels become smaller, except for what the studio wants to do to make them look pretty. They like big wheels. There's a reason for that. I'm not the right guy to ask. And then we can get to smaller powertrains. Smaller powertrains will get us to 54.5 in 10 years. What's important to realize is there's not one domain in the car that can do this by itself. It has to be done as a system. And that's part of why we need model-based systems engineering. Well, where do we manage all of these geometric parts, all of these performance things? Well, we manage those in Team Center. So it's kind of logical that Team Center, PLM, needs to embrace model-based system engineering. Let's talk a bit about models. When I'm talking to audiences that aren't familiar with what all you are familiar with, they get confused about what kind of models we have. Well, a model is any numeric representation of anything. And in the case of parts, it can be crankshafts and heads and other things. In case of assemblies, it can be a complete system. It might be a static mock-up. It could even be a dynamic mock-up. Wouldn't it be cool to see the accessory drive units in operation, see how they vibrate? Remember that energy equation, and we lost 70, whatever it was, % of the energy? A vibrating belt is a loss of energy. If you haven't designed the system well, those vibrations are going to show you where the energy losses are. It'd really be good if we could visualize everything in the assembly, including motion. CAE models, especially finite element models, I learned how to do that in the 70s. It was only a question of computers. We needed more and more and faster computers. We live in an age where we have computers now that just surprise all of us every day. Being able to do a very detailed analysis of the weak points in this particular case, and by the way, for anybody who's a competitor, these are all really old pictures, so you can take pictures all you want because we're way past this. But anyways, the red areas just shows you where the weakness in the design is. One thing we require at General Motors is that all of our engineers be designed for Six Sigma. That means you understand how robust your part is. What does that mean? It means that you are able to withstand the noises, the unexpected things that can happen to your engine block in this case. Another type of model is control algorithm models. I'm a controls guy in an aerospace program. I thought I wanted to help the next generation get to the next planet. And then I thought the astronaut Cernan explained it really well this morning about what happened, so I won't repeat it. So a lot of aero guys are in automobiles because at least we get to drive what we work on. Anyways, control models, algorithms to control an engine, algorithms to control a transmission, a lot of that's done in Simulink today or in some other modeling. But the model on the right lower side is a model of one of our older transmissions. It was one of the first models we worked with Jan and his company to understand that what we really want to do is integrate the two. I want to be able to take a Simulink model and put it inside the AIMSIM model so that I can do some closed loop learning on how this all works. Now, any of you playing with AIMSIM and with Simulink, you already know this all works, and it works really well, and it's true. I think the first time I was in Strasbourg speaking with Jan, I used this exact same slide. It's kind of old. Okay, I want to talk a bit about product complexity. You folks, as consumers, you buy cars because they have new features. Those features maybe get you fuel economy, maybe they get you a more pleasant ride, maybe they just have the latest cool technology. Though, as you go up the axis on the left-hand side, the technologies drive complexity. And what I'm trying to show is the various computer-aided things, computer-aided design, computer-aided engineering, knowledge-based engineering. We even coined a term for a while, embedding knowledge in the math tools, so rules about how things get done. Those are all curves along time. We call them hype curves. If you're talking to a business guy, they are very familiar with these things. There's always a lot of hype, how good it's going to be, and then there's always a drop-off, and then you finally get good at it, and it eventually gets mature. Our point about all of these is they're very necessary today. You wouldn't dream of doing engineering without them. But you also need to realize that combining them all, doing model-based system engineering is really needed for virtual vehicle integration. The dynamics I talked about, I want to see that belt going around the engine, as well as just the control system. You will see examples in this workshop where there's the ideal car with all control and a car that spins out of control, and they're overlaid on top of each other. Isn't that a cool context? You can see the vehicle, the product under control, and it maneuvers the corner. And if you don't have the active control, you can see that it'll spin out of control. That's what's really cool about all of the computer power we have today is you can evaluate products virtually without building any hardware. The other thing model-based system engineering needs to do is go cross-domain. We have all of our experts. In fact, we have lots of experts on each domain, you know, from noise and vibe to thermodynamics to structural durability to controllability to disaster recovery and other things, right? How do you bring that all together? The vision laid out by LMS and how to do this cross-domain sharing even before you have geometry so that you can even synthesize the design. That's where you get cross-domain dynamics, virtual customer experience. You can even start to assess drivability. Drivability to us is whether you enjoy driving the car. If you like a sports car, you might enjoy a hard shift. If you are really in a luxury car, you probably never want to feel a hard shift, right? It's really important to evaluate that without physical prototypes. Now, we'll always have some physical prototypes. After all, that's what you buy. But to do a lot of that work without them just makes it faster to market. And then as companies evolve, as these capabilities evolve in tools, the company has to evolve with it. So bridging these virtual communities is really important, and getting them to see the benefits in changing their work processes in order to take advantage of the next set of decisions they can make. This is a slide that we originally got from General Electric in Cincinnati quite a while ago now, 2003 it says. And all it shows is, you know, the classic car company was all about the road, right? And I want to go just build one and go for a drive. I was an aerospace engineer for the first 12 years of my career, and I moved back to the Midwest to work in automobiles. And of course, I'm a NASA and aircraft guy, right? I'm expecting simulations. And I get to Kokomo, Indiana, and I start asking somebody, where's their model-based development? And this is 1989. And they're like, what are you talking about? We can just go build one and take it for a drive. Why would we go model it when we can just go drive one? Of course, this is long before people started to understand variation, and I'll talk about that in a little bit. But in a culture that really wanted to go for a drive, they had to wait for the test vehicle to be built. They even had laboratories, but the laboratories were kind of one-off physical principle laboratories. I want to go discover something, right? It wasn't about, can I have a repeatable test? Can I have a repeatable understanding of the physics? Road to lab to math, it's also called systems engineering, analysis leads design. It's really important to do that. It's much, much cheaper, and that's the green and yellow lines here. It's much, much cheaper to find the problems up front. And then your laboratory and road work, it's just a confirmation that what you've done is going to work really well. We started the Road to Lab to Math strategy over a decade ago, and it was all about taking experiences from the road and putting them into at least a laboratory, and if not into a laboratory, put them all the way back to math. As computers got faster, as we worked with many of the CAE vendors, we were able to improve their codes to be accurate reflections. And so Road to Lab to Math was all about improving our time to market, improving our efficiency, and fundamentally improving our understanding of how the system works in all conditions. It's always good to define some metrics. Those were ours. And one of the biggest ones was to eliminate mule vehicles. Mule vehicles to us are cobbled together things that are fun to build, but frankly don't represent anything because they're built out of whatever parts you got on the cabinet. They're usually for a specific reason, a specific evaluation, but they don't resemble the final product at all. We have one example. Again, this isn't recent, but it just drives home the point where simulation really helps. We took 10 weeks out of our product development cycle by doing a lot more simulation and a lot less laboratory work. And in fact, the car work shrunk to about 40% of what it was originally. This is a big deal in a car company. This is significant dollars when you can take out this kind of time on your critical path. That has only continued. Candidly, we're not willing to share with you how much. We'll just tell you that we keep doing more and more in math, and we'll let the consumers speak about our products. You know, virtual engineering is advancing the practice, but I'm one of those guys that is never satisfied, and so I want more. And so think about robustness for a second. If we could keep the product model fidelity in tune with what we know, what else could you do with those models? This whole task called calibration, so the fine-tuning of the car so you find it pleasurable, that we could start to do in math. That we are doing in math. We do the final part in a physical test, but a lot of it's done in math now. Imagine doing system robustness studies. Well, I don't know how it's going to fail, but let's just suppose that it's going to fail a certain way. What would it do to the rest of the car? That's better systems engineering. Studying this in simulation is easy. Right? Give me enough computers, give me a little bit of time, and I can go study all kinds of side effects that you could never do through failure testing of mechanical parts. As I get field results back, durability results, what's failing in the field, I ought to be able to figure out what was the root cause and explore it. Was it a misunderstanding of the physics? Was it just poor material from a supplier? Or was it something else altogether different? And then finally, as big data is emerging, analytics on field performance is really, really, really interesting. We've done that forever. It's just that it's really easy to do it now. We can collect data from all your cars. If you're driving a Volt or the Cadillac ELR, you signed up for us monitoring the battery packs, and we monitor that a lot. Analytics on field performance data is going to be really, really powerful. Big data, that whole topic. We are going to see better products in all parts of our lives thanks to analytics. And then what about variation? This is a really old slide, but it's all about improving understanding. Your field variation is something. You should measure it. You should know what it is. Your lab variation might be something else, and it might be too expensive to move your lab on top of your field data, right? But it's important that you understand what you're learning. Model variation can go anywhere, right? It's just a few adjustment of parameters, and you can study all kinds of things. So one of my points is we will, and we have, and so will my competitors, will keep exploring robustness by doing variation. Variation, being able to adjust parameters a little bit this way, a little bit that way, is a strength of simulation. Doing it over and over and over is relatively inexpensive. On the other hand, that generates an awful lot of data. We have a lot of test data as it is. So how shall we manage the findings in a way that enables faster product development? I've even heard the words today from the leaders at Siemens, and I'm really pleased to hear it. As we learn either physical testing or field data, we want to be able to quickly adjust our models, our plant models, our understanding models. It's really important that feedback get there. You know, for a while it was all about, can I model the physics? Well, we made that. So now, can you model the physics when you learn something surprising? That's where we're at now. Managing all that data is important. Now, I've been working with both LMS and Imagine Lab and the Team Center guys now upwards of a decade, and I'm just ecstatic with the way things are going. Siemens will talk to you more about this during the week, but what I want to emphasize to you is the 1X and 100X. They understand what we understand, the speed with which you can do an evaluation. And also, as you see there on the right, there are many other tools we use. That will always be true, whether it's a particular physics modeling package or a different way of modeling, managing models. For those of you that know autonomy, it's a part of a Department of Energy initiative that a few years ago now, LMS agreed to help distribute and get out to the rest of us. And the rest are there. Managing all that information is one of the next steps, and I'm pleased to see that it's actually happening. And then I saw a demo earlier this afternoon of this exact example, and what I want you to just realize is, look what's connected. It's not just the design anymore or some load cases, but it's also the understanding of what happens as you go through the maneuver. And we're managing it in an architecture of models that's represented back in Team Center, and together they work. This is great. This is what it should be. Let's talk about controls. So when I say controls, I don't necessarily mean factory controls. This audience might think that. I actually mean the software that's in your cars today that helps manage acceleration or fuel injection or whatever. General Motors decided 20 years ago to build its own internal software organization. I was a part of the hiring when we did that. A few years ago, the count was 3,000 contributing engineers, lots of variants, millions of lines of code, millions of product instances per year, tens of thousands of unique product variants. As we've talked with Siemens about product variation and how do you manage that variation, they've, to their credit, have come and understood what we do in this space and have realized that this variation makes mechanical variation pale by comparison. Of course, we got all kinds of regulations around the world. That's the price of being a global company. And there's all kinds of economic pressures that we've been through. So you might ask yourself, why would we make this kind of investment? This is a study that DARPA did that just flabbergasted me. So take a moment to look at it. The x-axis is a measure of complexity. So it's source lines of code and part counts, so electrical part counts in this case. And the the vertical axis is time to market. So all you aerospace guys, pay attention. That blue domain is where you guys are. You know, they want more, and they got more requirements, and they got to be specific about those requirements. So it's just going to always take longer. By the way, that's a log. You guys probably, how many people remember a log graph? This is a log graph, okay? It's really scary if you do it in a linear graph. The thing just goes out of control. It's a log graph. So the red is the silicon industry. So they're able to add complexity but not increase time. The green is the automobile business. Let that sink in. Why do you think all the rocket engineers are working for the car companies? How do we make a car that you want to buy without it actually decreasing time to market a little bit, not a lot? The people like to bring up this faster, higher quality, or lower cost. You get 2 out of 3. The successful products companies, wherever you are, you figure out how to do all 3. That's why that green line is going down. There's only really one way to do that, and it's massive reuse. Reuse of knowledge, reuse of parts, reuse of other assets between parts and knowledge. And I'm not saying everybody wants a reused thing, but at the end of the day, what you're interested in a commercial product is that it does what you want. And yet you pay for the things that make it unique, and you don't pay for all the rest. And ideally, you get it first, because at least here in the States, we like bragging rights, and you will buy it from ourselves or from one of our competitors based on that availability. The reason DARPA contacted General Motors is they wanted to know, how is it you guys do this green thing? How is it you can bring a product to market a little less time that's orders of magnitude more complex? And the answer is simply product line engineering. And if you're not sure what I'm talking about, I'm not the expert, but there are lots of people that are. Just start Googling it. Okay. So when the US government comes and asks you, hey, how do you guys do this? It makes you think a bit about maybe we're doing something pretty good. These controls guys that I was was nice to be with them the first 10 years. The second 10 years at GM, I've been doing this other thing. But let's talk about a system of systems for a moment. Imagine you've got the R&D guys, they're coming up with a new idea for a feature. Then they put it into a standard solution of products, the product line, okay? That product line gets instantiated in a particular kind of embedded computer. So those are 3 kinds of controllers. You figure out which of those is best fit for your vehicle application, if it's a truck or if it's a small car or if it's some big truck with lots of cylinders. And then you manage the change that goes with that. So the way that feels is like this. Solutions are developed and implemented capable for use on any vehicle globally. Managing a product line means you're thinking about all of your customers. Increasing individual feature development costs, that's true. Getting the feature out the first time takes a bit more time and money. But at lower cost for the system it goes into. The second, third, fourth, and fifth use of that particular feature is much, much faster. That's why the green line goes down in slope. Standard reused components. Once these controllers, in this case, were developed and validated, then we can reuse them in other products. You don't really care what kind of computer is in your car. You know, you used to get a kick out of the computers that had the Intel logo on them, right? Because for a while you cared, I guess. But you don't really care. You just care that it works forever. Then you apply it to a particular car. That's an application engineering job. So you have a couple choices. You're not painted into a corner, because over there in the product line, there's all kinds of choices. Okay? And then you have a really rigorous change process. Rigorous just means that you're thinking about the whole product line all the time. It really is a system of systems. So if you're designing a family of systems, a product line, if you will, you'll think about the change to that upper crossover vehicle and as it affects the Suburban in the bottom. That may seem inefficient to you. The efficiency comes when you look at our scale, right? And all the numbers of products that can have that. Okay, the tool implications of this are significant, and we'll come back to that. Calibration used to be a thing you did in the car. It was a heck of a lot of fun driving around. It's also mind-numbing when you couldn't reproduce a problem, right? Simulation can make that much faster. We have been using CAE tools now going on 10 years to do algorithm development and calibration concurrent with hardware development. In the past, it was always a serial process. Quality has improved dramatically. Time to market has improved a little bit. The controls guys, I was talking about that product line engineering. This V chart is important in its colors, and it's the one thing I want you to take away. If it's blue, the light blue, that's what goes in your car. If it's pinkish, that's what's common across the globe. And if it's a bit of the green, well, there's not one of them, there's maybe a couple, okay? But imagine how we manage this across portfolio management, requirements management, and system safety management for our fleet of vehicles. There's a cadence of programs. We have our own timing for how we put control features, make them available, if you will. And then an individual vehicle program comes along and decides which ones to pick up. Okay. Now, I always challenge the tool suppliers. I usually get a lot of thanks afterwards about what's going well and what needs help. And one of the things about GM is we're big. We're in many countries. And in fact, we've got team center databases all over the place. The green ones are ours, the orange ones are our JVs, and some of the biggest tier ones also are pretty connected to us or through databases we manage. This is complicated. Those of you that have been with us with Team Center, you know we and the Siemens guys, we have this nailed really well. We're really quite good at it. And Team Center for sure is the backbone of making the global enterprise work. We're in Team Center Unified. You want to know more details, we got several people here this week, just ask one of them. Okay, but how do you bring together all of these tools into a plan? I became the PLM leader to solve this problem, right? How do we get integrated PLM tools? How do we have an integrated change process? Not just what we did for controls, but do it across all things in engineering. In fact, all things across the life cycle. Take a close look at this picture. It goes from the initial requirement to the way we want to build it, a product line, that's a constraint, to a particular product definition, does it meet a market demand 5 years in the future, to all the work we do virtually, followed by all the work we do physically, followed by mass produce it for a few years, and then you drive it for, well, right now, 10, 12, 13 years. And then you bring it back for recycling, and throughout that whole process, knowledge is gained. What are the implications to the PLM tools to pull this all off? Remember, I want to do model-based simulation throughout. I want to be able to gather knowledge as we learn it. By the way, you really got to clean up your master data if you haven't already. Team Center applies to this part of our domain. We have big initiatives going on in General Motors to take advantage of Team Center in the CAD space. That's where it has historically been, but expand it way out beyond that. Some of the people speaking this week can start to tell you about that journey. Of course, the enterprise ERP side of the business, The new GM, we're trying to redo many of the things in our back office, and there's lots of work being done with SAP in that front. How we integrate Teamcenter and SAP will be really critical. Active Workspace is key to getting us the integrated change process in a simple to use, ultimately tablet form that's usable anywhere. And also this other thing that got covered up on-demand visual BOM. You know, right now, if you want to build a mule vehicle, I might have to wait 3 months, maybe an integration vehicle, 8 weeks. If I want to build a virtual assembly, it's still on the order of days. So it's really annoying because with all these computers and everything else we have, why can't I get an on-demand visual BOM? If you want to know why 4G exists, it's that reason. And Siemens explains it better than I do. But we have to be able to enable that to enable model-based system engineering. I mentioned the ECS tools. They're not part of the Teamcenter suite. They're a different set of vendors. They go through the life cycle into sales and service. There's also a way to manage all of this work happening in engineering. It's called the process of engineering. And finally, as all of you know, big data is on the scene, and big data is enabled largely by tools like Hadoop, as well as all kinds of just inexpensive ways to recategorize and study data patterns. It's really, really, really kind of interesting. There's also a lot of work. Clean up your master data. If you can't clean that up, your big data won't help you much. At the end of the day, it's all about the right information to the right people at just the right time. The just right time comes from the process of engineering. The right people comes from role-based actions and workflows. And the right information comes from context. I need to know the context of what I'm looking at. Both Chuck and Eric and some of the other presentations this morning talked about the flexibility in looking at that context. It's right on. That's what we want. That's what we want. You will do a better job engineering if you understand those different contexts. So I've said many of these things. I won't repeat them. GM's PLM architecture is Teamcenter globally. I will say, once we understand more about what the data is telling us, then we want to improve the fidelity of models. We have lots of learning loops. And then get after robustness studies. It's becoming really affordable to do all kinds of studies of what's possible, even the way to synthesize a car. I'm serious, synthesize a car. I don't have to design it anymore. I can take fundamental principles and synthesize it. That's because computers are cheap and cheaper every day. We would include sensitivity to manufacturing variation. At the end of the day, we're a big manufacturing company that sells a lot of products to you all. Understanding the process capability inside a factory is really, really, really key. You'll get other variations. Sometimes you get variation in a brand new market. You get variation you didn't expect, right? You did all these load cases for Europe, the United States. You're like, got it nailed. I can sell the product anywhere. And then you find out the roads in another part of the world are just really different. Adjusting and shifting the variation. You know, DFSS teaches you, well, if you don't like your robustness, shift the problem, right? Come up with a different design that puts the noise somewhere else in the system. The best goal is get rid of the noise, because that's an efficiency thing. And then customers, especially generational differences, customers use our products differently. It's really important to stay on top of that. Siemens, the future of PLM is fast approaching. Active Workspace is a key part of that. I got a couple examples just in the last days, just showing you what's possible, right? Before, you had to count on a bunch of other infrastructure to show you a piece of the front assembly for the suspension system. Today, you can query, and it quickly just shows it to you. You also see related parts on the left with some key attributes about those parts. And as the Siemens guys, as they do demos, I think Chris is doing demos on some of this later in the week, make time for it. It's in context, it's on demand, it's right away. I heard a presentation earlier today about you don't know where to find it. That's okay, put in a partial name, you'll find a piece of it. Think middle out, don't think top down. Someday I'm going to write a lecture about the V and why the V doesn't work for big companies, because it really is about middle out. What do I mean? You have existing stuff on the shelf. It's really good stuff. It works really well. You don't redesign that just because you have a new product need. You try very hard to reuse that. That's what I mean by middle out. And at the end of the day, you're just trying to improve the decisions, right? Whether I'm here and somebody else is in Detroit and another guy is down in Brazil, we should be able to work together on fixing that yellow part, whatever its failure is. Computers, visualization, they all help do that. Remember that V cycle I showed you? Don't think about it anymore other than to say, I really want it integrated really, really tightly. Does that mean the tools exchange data? Oh, I don't know. I think there are different technologies coming at us from all angles. The web, the way the internet works, has been teaching a lot of people about how to actually exchange data. It's not point-to-point anymore. There is something called the Linked Data Framework. Both Siemens and IBM have embraced it. Other ALM vendors, I think some are actually here, Polarian in particular, and Electric Cloud, they also are embracing it. We're pretty sure that this will work for General Motors. We've started work to do demonstrations of it. We admit we're not the experts at this. We're counting on our tool vendors to figure that out. We will do demonstrations this year and next to figure it out. And then finally, improving the systems focus across the life cycle. General Motors is a little behind some of our competitors at looking at systems-driven product development. But let me point out the things I'm really pleased to see in it. I'm really pleased to see product line engineering. I've been working for the last couple years with the Siemens principals on exactly that and what it means. It's that green line going down on that DARPA chart. That's why it's so gosh darn important to everybody. Doing multi-domain traceability and configuration. A lot of government contracts, you have these traceability requirements. Tell me how this requirement affects that system and vice versa. How does the system affect that requirement? It is a discipline of system engineering to understand that traceability. Well, evolve from that, right? Wouldn't it be cool to see the traceability all the time in some kind of active network of, as you apply a load case, different requirements become more or less sensitive? Think about what that would look like. Think how you could make better decisions if you had that. These are a couple other of the Siemens slides. I get the privilege of seeing a lot of their future plans. I got their permission to just put them in here to say they do have it really figured out. Of course, we're developing it together, and some of you, and how you roll it out in your company. I gave a presentation earlier with Paul Nelson from Orbital ATK, and we were pointing out the differences, right? You won't roll these out in a particular way. It depends on your company, and you have to figure that out. But the fact that somebody with tool capability, with expertise in developing tools is figuring it out is really, really, really good news. And finally, we are aware of it. Some of us, I think, had influence on it early on, but at General Motors in general, this wasn't our focus. It will be our focus next, but next is probably over the next few years. Our focus now is on integrated product development, as Siemens calls it, and active workspace, and the things related to that. Okay, I'll go through some of this quickly. So the ELR has a big battery pack in it. You will not design that through trial and error. Just not humanly possible. So we said, let's model it in SysML, and better yet, let's put all the bill of process, manufacturing process things we've learned about making these battery packs. So there's thermal bill of process, there's a module bill of process, there's an electrical bill of process. Let's put all that into SysML, and let's also connect it to NX. We did this a few years ago. So in NX, there's ways to check these BOPs, to check that the design that has been envisioned and packaged into a particular vehicle, in fact, still meets all these other constraints. In fact, we got to the place where we automated it, and so we could synthesize the battery pack configuration. For those of you that don't remember, we buy cells, but we make the overall assembly. And our conclusion a couple years ago was there's a tremendous amount of work to make MBSE and SysML, or even Modelica if you're in that camp, and the IT and engineering environments work together. It's not just a tool thing. There's lots of other things that have to happen too. It needs to be a conscientious effort with IT and the PLM industry, and that is happening, I'm pleased to say. And we'll be glad to keep helping out. We won't do SysML everywhere. If you've got all of these existing parts on the shelf or existing knowledge on the shelf, do you need to go model all that in a language? May not be worth it if you're really, really good at that particular subsystem. On to products. So are we any good at system engineering? Well, of all of these listed, it's better when other people tell you. And the one I wanted to highlight was, if you haven't driven a 2014 or 15 Chevy Impala, you should, because it is the highest rated sedan ever, anywhere. Nobody expected General Motors to do that. And as I said, everything starts and ends with great products. Here's a couple others. Those of you that took my earlier assignment, you should know that the 2016 Camaro looks nothing like the upper right-hand picture. If you haven't looked, take a look. Headlamps are different. The front end is much more aggressive, and we hope you like it. And with that, I think I have one more. Oh, yep. We were pleasantly surprised this year with Motor Trend's Truck of the Year. That's our Colorado. The car business is hot and heavy all the time. We're at each other's throats trying to win these awards. And this one actually was unanimous, which doesn't happen very often. So if you haven't read, these come out in the winter. If you haven't read the Motor Trend article, we encourage you to do that. If you're looking for a really good fuel economy pickup truck, go buy one. And I'm Craig Brown. I'm the PLM leader for General Motors. We have a vision. It's around these 4 themes. It'll drive our investments over the next few years. And maybe I'll come back and tell you how we're doing on these. The words are important. Connect people with information. I didn't say integrate a bunch of databases. I said connect people with information. Make it visual. I mean more than a static display. The static displays are great, okay? But go further. Show me dynamics. Show me energy losses. Foster innovative vehicle development. Our CEO has made it crystal clear we intend to be the most valuable car company in the world, and we intend to have the best products forever. Hold us to it. And finally, PLM can and should accelerate customer-focused decisions. The car customer, the people buying our cars. As you guys think about tools and the evolution of tools, put the customer, put the car-buying public at the center of everything you're thinking about, and we will accelerate customer-focused decisions. With that, I think I have one more thing for you to see. Don't ever be the same. Thank you.